Right, folks. Well, we're a few minutes after the top of the hour, and it is time for the September edition of Datadog On. This is a super special episode of Datadog On because, as you'll hear later in the episode, it's a 2.0 of our eBPF episode that we recorded almost a year ago. I think it might have even been more than a year ago, but you'll hear from that. You'll hear from our guests on that in the episode itself. This is Datadog On Maintaining eBPF at Scale. So if you're not familiar with Datadog On is a series where we invite engineers working at Datadog on things at Datadog to talk to us about a specific technology or an interesting engineering problem that we've kind of solved internally and also often solve for our customers as well. The recordings will be available on datadoghq.com. Just a couple of housekeeping items, though, before we get started with the episode. This is a live episode, and it is, of course, made better by your interaction with us, right? So we want you to engage with us using that Q&A button in Zoom to ask us questions as we're going through, and I'll keep an eye on that. And if your question is compelling and interesting, we'll actually just pull the handbrake on this episode and we will answer that question live. So please do find that Q&A button right down at the bottom of the Zoom and use that to ask us questions. You're welcome to even direct questions to a specific panelist, and you'll hear about our awesome guests here in just a few minutes. So let's get right to it. If you are not familiar with Datadog, Datadog is an essential monitoring and security platform for cloud applications. We bring together what we call those three pillars of observability: end-to-end traces, metrics, and logs. And that makes your applications as customers, your infrastructure and third-party services entirely observable. And as a side effect, also secure if you happen to be one of the customers of our awesome security products. I'm joined today by two fantastic guests who I'm really excited to have here with me today. I'll let them introduce themselves here in just a second. But these guys are coming in after hours. They're both based in Tel Aviv. So Val, do you want to go ahead and introduce yourself to the audience?
Yes, thank you, Andrew. Hi, my name is Val. I'm a staff engineer at Datadog, focusing mostly on eBPF domain and helping growing and improving multiple Datadog products which use eBPF as an underlying technology. I've joined Datadog a bit more than a year ago, following acquisition of a secret startup where I was the CTO and co-founder. Secret was developing an API management platform for our customers, and we actually also use the eBPF technology as underlying technology for the secret agent.
Great, and we're also joined today by Guy, who I will go ahead and let introduce himself as well.
Thank you, Andrew. So, hi, I'm Guy. I'm an engineering manager of the recent product here at Datadog. I joined Datadog with Valeri after the secret acquisition last year. And since then, I'm leading the development of Universal Service Monitoring, USM, that aims to allow users to get service health visibility into services running on their infrastructure without touching a single line of code. All that by using the eBPF technology to passively inspect and process packet data on the machine.
Nice. Well, welcome to both of you, and thanks so much for being on this episode of Datadog On. I am Andrew Krug. I am an engineering manager at Datadog as well. I lead the security advocacy team at Datadog, which is primarily responsible for things like Datadog security labs and a lot of the conference talks you see on stages kind of all over the world. We also do things like the state of AWS security and upcoming other fun and interesting research reports. But I think what's really interesting about these episodes is that we talk about how we do things from an engineering perspective at Datadog, because Datadog's scale is incredibly large, right? We have tons of customers, we have millions of hosts inside of Datadog, and we have trillions of data points a day coming into the Datadog platform. So oftentimes the things that we encounter are things that no one else has seen before, just kind of due to the scale and the way that we think about building things. Notably, there is a previous episode of Datadog on eBPF. Like I said, this is kind of the 2.0 of that episode. And if you want to check out that original that was led by a colleague of mine, Ara Polito, that's a great just general primer on eBPF. And we're going to look at some similar slides today, but the goal here is really to dive deeper on a couple of specific concerns with regard to just like how we handle all of the different eBPF probes and monitoring that the Datadog agent does for us and for our customers. Any thoughts on that previous episode, Val or Guy, before we dive in here?
Yeah, so I think that was actually a really good episode describing some baselines and basic topics of what is eBPF and how it can be leveraged for cloud monitoring usages. I think it will be interesting to see, given the time passed between those episodes, how Datadog evolved in using eBPF and what are the new challenges that we are facing over time is expanding and leveraging more and more this wonderful technology.
Yeah, and as we go through again, don't be afraid to hit the Q&A button and ask questions of our great guests here. You've got folks that are the authority on this domain at Datadog. So bring us your challenging questions as we kind of pick this topic apart. But with that, I'm going to hand it off to Val to talk a little bit about just what is this thing that we call eBPF.
Yeah, thank you. So just a quick recap before we deep dive into particular topics of scale complexities. Let's just have a reminder that eBPF is a set of technologies that can run sandbox programs in the Linux kernel without actually changing any kernel source code or having to load some kernel modules. eBPF basically stands for Extended Berkeley Packet Filter. And as the name suggests, the old ancestor of eBPF is plain BPF. This technology was introduced way back in 1992. There was some work that was done by Van Jacobson to troubleshoot some network issues using network filters. So as I said, BPF originally stood for Berkeley Packet Filter, but in 2014, eBPF was introduced in Linux kernel. And nowadays, this can be done much more than just packet filtering. So the acronym is no longer actually valid or makes sense. eBPF is considered now as a standalone term that doesn't stand just for the network processing. In the Linux source code, the term BPF still persists, and in tooling and documentation as well. Terms of BPF and BPF are generally used interchangeably. The original BPF, funny fact, sometimes referred as CBPF, which stands for Classic BPF, just to distinguish it from eBPF.
Yeah, so before this, people were doing all kinds of crazy things, right? Every time that you wanted to really extend the functionality of the kernel for monitoring, you'd have to write a custom kernel module and compile it. And that was kind of a painful process, also somewhat dangerous to hot load custom source code into the Linux kernel for things like instrumentation and monitoring.
Yeah, that's true. And also don't forget that when you're developing a kernel module, you also need to go through the signing procedure because you cannot just load kernel modules freely in the Linux kernel.
I think the last time I was a kernel module developer was pre-signing. So,
yeah, that's true.
You just wrote that code and tossed it over the fence at the kernel, and it just trusted it. But I think those were like 3.x kind of days.
Yeah.
We use eBPF at Datadog for a variety of things, right? So why don't you give us some context just about kind of how Datadog has leveraged this technology in the Linux kernel to kind of build out our monitoring platform.
Right. So in the recent years, eBPF emerged as the new cool kid in town, in both trending and evolving technology, and gains more and more popularity and usage worldwide. At Datadog, eBPF also gained wider adoption, and there are multiple products are using it as an underlying technology to capture raw data in more efficient and more scalable way. Today, we are using eBPF in several different Datadog products in different domains, such as observability, security, and even dev tools. So for example, here we can see 5 different teams and products that are leveraging eBPF technology. NPM, which stands for Network Performance Monitoring, and USM, where Guy comes from, stands for Universal Service Monitoring, are both observability products that capture different layers of network stack using eBPF. CWS, which is Cloud Workload Security, is a runtime security product that leverages eBPF to capture different events happening on the host and then detecting and preventing anomalies. There's a processes product that allows us to capture running processes and containers in the cloud environment to bring the visibility to our customers. And as I said, last but not least, dynamic instrumentation, which is a dev tool, allows production debugging capabilities for developers, cloud applications, without needing to redeploy or changing lines of code of the application. And for some programming languages, we're also utilizing eBPF technology to capture application context in runtime and present it to our customers. So given the increasing usage of eBPF, more and more products, as you can see, are using it inside Datadog, we also formed an eBPF platform team that owns the infrastructure of eBPF at Datadog and helps to improve the velocity of engineering teams.
So given that's a whole bunch of data that we're bringing in, right? It's almost all of the parts of the observability stack that we can instrument with eBPF probes inside of Datadog. What is the difference, from our perspective, on who works on the platform team versus who works on these specific products? Like, what's the difference in the day-to-day?
Yeah, that's a good question. So naturally, product engineering teams are building customer-facing products and leveraging this eBPF technology as underlying enabler for it. So today, as I said, we use it for monitoring, security, and dev tools, and to allow better development experience and increase the velocity. We formed a platform team to take ownership on some common problems in the eBPF space and help create this infrastructure capabilities. This platform team is actually working very closely with the engineering teams to help solve some of the most complex problems and create the next generation infrastructure.
And we're going to hear more about some of those challenges, I know, later on in the episode. I don't want to reveal too much here, but I think maybe next you could just kind of give us some context about how we manage the lifecycle of eBPF programs, particularly in something like the Datadog agent, right? Because the Datadog agent, 100% open source, touches tons and tons of customer systems, but I bet there's a lot of thought that goes into just kind of managing the lifecycle of that code and making sure it's both forward compatible and backwards compatible with all of these variants of the Linux kernel that we have to support over time.
Yes, you're absolutely correct. So this is a general diagram of eBPF program lifecycle. And during this episode, we are going to deep dive into different phases of this process and discuss multiple challenges that we face as Datadog engineers and how we trying to cope and solve some of them. And so this is like a quick agenda for some scale challenges that we have in eBPF domain. So the graph here is trying to show that we have a basically multi-dimensional problem space, and given the large amount of customers that we're facing at Datadog, we have a lot of different challenges in this matrix. So first of all, of course, we need to support a lot of different cloud environments, whether those are Kubernetes, different cloud providers, EKS, JKE, or AKS, or it's containers, or even like non-containerized environments, Docker, Docker Compose, ECS, and much more. Secondly, so speaking in eBPF context, as a native technology of Linux operating system, we also must support different Linux distributions that sometimes affect the behavior and usage of eBPF subsystem. So just an example of some of those distributions contain Ubuntu, AWS, Amazon Machine Instance, Fedora, Debian, and there are more. And lastly, of course, Linux kernel, similar to any technology, is also evolving, and there are new kernel versions that are being released. Unfortunately, in the real world, not all the customers are using the latest and greatest Linux kernels, and that means that for us, we need to support a long tail of old kernel versions and to be able to run our eBPF-based products on those customer environments. Since, as you said, Andrew, we are having a Datadog agent, which is an open source that runs on customers' environments, and that's where we are utilizing eBPF code. So to bring a couple of examples in this slide, and then we will touch base those in more details later on. So initially, eBPF was introduced in kernel 3.18. The full use of eBPF actually requires at least kernel 4.4. Datadog has some of the older products based on eBPF that actually supports even the oldest kernel versions, such as 4.4. However, there are some products that were introduced more recently, and they are supported. The minimal version that's supported for them is actually a bit newer, if I might say. It's 4.14. Just a fun fact, 4.14, the end of line is going to be very soon, beginning of the next year. So we're talking about like still very, very old kernels. Last thing that I try to emphasize in this slide is the fact that we are running Datadog agent on customers' environments, and we are being actually hosted and utilizing our customers' resources such as CPU and memory. This brings us the fact that we need to design our agent with hard limits for resource utilization in mind to avoid excessive usage and noisy neighbor scenarios. So here actually eBPF comes very handy as it allows us much more efficient operation because we can shift some of the logic to the in-kernel execution probes. But we are still facing continuous challenges dealing with enormous amount of data that requires extra filtering and being extra cautious when we deploy new agent versions. So overall, in the next slide, we will try to explain in more details each one of those topics and see how different tooling help us to resolve these problems.
So yeah, that's a whole mess of information. A lot of challenges maintaining the old and the new. I actually don't. It feels like I've been doing this a long time because Linux kernel 4 doesn't really feel like it came out that long ago. But I guess basically in lifetimes, we're talking about, you know, it's Linux kernel 4 is as old as Windows 8 at this point. So it's actually quite a while ago. And I don't think this is a problem that gets easier as time and additional kernel variants and flavors of Linux proliferate, right? Because as we think about backwards and forwards compatibility, this just gets harder and harder, kind of the more kernels you have out there. So let's talk more about that.
Okay. So Valeri showed you the eBPF program lifecycle diagram. It will for us. We will use that in the presentation. And let's start and talk about the lifecycle of the eBPF program. We all start with a development machine and a source code and a supported compiler. It's probably a Clang. And from that source code and using that compiler, we are able to generate the eBPF program, which contains eBPF bytecode. Now, on the target machine, which can be the same as the development machine, but can be different as well, we are loading the eBPF program into the kernel using the BPF syscall, and then we are reaching into the kernel part, and we're meeting the first component in the process. It's called the verifier. It's a very, but I think Valeri will talk about it later. But it's a very complex component, and its goal is to ensure our code cannot harm the machine, and our program is a final program, meaning we cannot run forever and block kernel functions, and we cannot cause panic and crash the kernel in the machine. After the verifier, we have the JIT compiler, a just-in-time compiler that makes the final optimizations and loads the instruction, the BPF bytecode into instructions and apply our hooks. And for my part, the focus will be on the highlighted rectangle, and every solution we will show will be scoped to that highlighted area. Okay, so most of the eBPF programs are inspecting kernel functions, kernel structs, and their fields to be able to extract the relevant information. The fields of the same struct can be ordered differently between kernel versions and Linux distribution. For example, new fields can be introduced between new kernel versions. Some might be removed. Alignment can affect the offsets. Compilation flags of the specific kernel can introduce new or less flags. So we cannot know upfront where a single field in a specific struct is located. This is the difficulty of eBPF development, is to build a program so it will be portable and can run on various deployments that can have different Linux distributions, different Linux kernel, different compilation flags. And we are going to explore 3 different techniques we are using to handle that problem, and hopefully to have a portable eBPF code that can run on multiple deployments. In the previous episode, we discussed the first 2 methods, the offset guessing and the runtime compilation. So we will go over them as well, shorter than we did in the last time. And after that, we will deep dive into core technique. Before we start, one might ask why we need 3 different techniques to achieve the same goal. So as we will see, each method has its pros and cons. Some are improvements to the newer are improvement to the older one, but all methods are still have cons and they are not perfect. We are using in Datadog we are using the 3 of them in a fallback mechanism. Meaning we are starting with the newest, which is the core, and if in case of an error or failure, we are fallbacking to runtime compilation. In case of failure, we are fallbacking to prebuild. So this gives us some safety net that one of the methods will succeed. So let's start with the kernel offset guessing. In that method, we are compiling the eBPF source code on our development machine, and then we need to run the single eBPF program on multiple target machines. Now, on the target machine itself, we start the process of guessing the offset. For every kernel struct and field we are using, we build a test program that triggers a kernel function or syscall, and we are putting some predefined values in specific fields that we provide syscall. So the test eBPF program is trying to find the exact offset for a specific field by searching for the predefined value. We are doing that using iterative method to scan every possible offset from the beginning until we are finding what we are looking for, or we are exhausting all the research. The outcome for us is the mapping between the fields to their offsets in the struct. And at low time, We embed the offset mapping in a dedicated session in the program. We call it constant editing. And eventually, during runtime in the eBPF programs, we are accessible to those consts, and we can know exactly what is the offset for each field. So while it may sound good and simple, the method reveals many issues. The method it works great for simple structs and that we can control their values by syscalls. But if the struct is not exposed and it's fully internal, the problem becomes much harder. So this is the first issue. We are limited to specific struct, and we cannot apply it on all structs. And another issue is nested or complex structs. For example, the task struct. We might be needing multiple steps to get the desired offset, but it is more likely that we will not be able to get it at all. And the third problem is some kernel fields can have the same value, so we cannot know exactly what is the correct offset. This is the ambiguity issue. So now that we do understand the limitations of the program, the method, we can talk about the first improvement, the new the runtime compilation method. So the idea here is to compile the eBPF program on the target machine and rely on local kernel headers. It gives us the offsets that we need. We ship a signed source code along with a limited version of Clang. The limited version has only the BPF backend, and we do compile our source code at runtime on the target machine. On the machine, we are reading the BPF source code that we shipped with the agent, and we are verifying the signature to make sure that we only compile and load our known eBPF programs. We're trying to minimize the attack surface. We are loading the kernel headers, and we use them in the loading process using the BPF loader to get the offsets and make the relocations, and by that, removing the need for offset guessing. It might sound flawless, but actually there are a bunch of issues we are introducing. So there is no guarantee for the kernel headers to actually exist on the machine. So this is the first problem we needed to face, and it led us to develop and implement another step in the process, which downloads at runtime the correct kernel headers to the local machine. And it adds a lot of complexity to the agent, and it involves outbound connection from the agent, from the system probe, our component, our elevated component. And in some customer environments, it can be forbidden, and we cannot use the technique. For security reasons, the system probe component didn't have any outbound connection, and that method required some exceptions. So this is something we don't do usually in system probe, but we had to do that here. Another issue with the compiler is the compiler toolchain that we ship with the agent. So we need the Clang compiler and LLC, part of the LLVM, Clang LLVM combination, but the combination was too big for us to ship it and distribute it with our application, with the Dockers. So we decided to ship a stripped Clang LLVM toolchain with only BPF backend for the relevant programs that we need. The idea here is, once again, to reduce the potential attack surface and do not allow compiling any arbitrary code. So this method as well is not perfect. It improves the scenario compared to offset guessing, but it introduces other risks and problems that might not be easy to solve.
As somebody who has worked as a security engineer, the idea of a Linux machine compiling something on the fly using dev tools always sounded kind of suspicious to me. So I'm glad that this isn't the solution. That's the best solution, right?
Yeah. This is still common in the industry. We will just see the new and better solution. But until 2 years ago, this was I think the main use case for most of the, at least open source projects that I've seen. Okay. So let's move to the newest technique, the query. This is a relatively new improvement for eBPF, and the goal is to make every eBPF program truly portable. So we will not need to handle issues we talked about in the offset guessing on runtime compilations. And the basic idea is to compile the eBPF program once in the development machine, not on the target machine. And with the new kernel feature, we will be able to run and load it on every kernel. So as the name suggests, query is actually compile once, run everywhere. So to achieve that, we needed a new kernel feature that is called BPF type format file, a BTF file. The BTF file is shipped with any new Linux kernel, and that file replaces for us the need to have kernel headers or just the offsets. For us, it contains all kernel structs and their field and their offsets in the struct. So once the file exists, we don't need any other technique. So the entire process became much easier.
And so this relies on things being kind of predictable places in memory. So like BTF is kind of like debugging symbols, I guess, for eBPF. Would you classify it that way?
Yeah, this is a good classification. Eventually, instead of re-implementing, or this was an industry problem, and the community solved it by having kernel just exposes all the information we need, and you don't need to ship anything alongside your eBPF program, and it requires changes in the kernel, in the loader, in the compiler to make it available. Yeah. So here we compile the eBPF code on our development machine, and we ship the agent, we ship the bytecode program with the agent. On the target machine, we are looking for the local BTF file, and we use it in the loading process. And the eBPF deployment became almost fully portable. So yeah.
So I guess the follow-up question here to that would be, this sounds great, right? This idea that the kernel just comes with everything that I need in order to build these programs that are actually truly portable. I don't have to do offset guessing. I don't have to do runtime compilation. But what if you have a kernel or like a custom flavor of a kernel that doesn't come with a BTF file? What's the next step there? And is there a solution for compile once, run everywhere?
Yeah, so that's a good catch. I didn't specify it, but BTF was introduced, if I'm not mistaken, firstly in kernel 5.8. So it's not a recent kernel, but still it's not too old. So allegedly for kernels before that, we didn't have that support. That means that allegedly the implementation can be applied only to supported kernels. But the community started to backport the BTF file to new patches for old kernels. So now you can have, if you have the latest 5.4 or 5.2 kernel versions, you probably have a built-in BTF file. The Fedora distribution, Red Hat distribution, Fedora and CentOS started to backport it to 3.10 kernel. This is still, it was pretty common for CentOS and Fedora. So if you have, for most of the kernels, if you have the latest version, you will still have BTF, but still the hard kernels, or at least old versions for unsupported kernels, that still doesn't have BTF. For example, 4.14 or 4.4, already mentioned, they do not have BTF.
I assume this is primarily used for long-term support releases. Like you said, folks still running kernel 3.10, which is probably like CentOS 6, I want to say.
I think 6 and 7 as well, but I'm not sure about it.
Pre-system D Linux.
Yeah. the community did solve the issue we just discussed about. So for such kernel that we don't have a built-in BTF, or the newest patch for that kernel doesn't have BTF, we have the ability to still create a BTF for it. I think 2 years ago, a new community project started. It's still called BTF Hub. It's a repository and tools to generate BTFs for all kernels. So it gives us the ability to take an unsupported kernel and make it somehow supported. And so we can create a BTFs for those unsupported kernels. We can do that offline, and we can create in a continuous process for every new patch for the unsupported kernels. It's pretty common and quite handy for 4.14 kernel that is still widely used. What we can do is we can ship the BTFs along with the agent, so we can have a broad support and broad coverage for all kernels, or most of the kernels that we are seeing. The one problem is BTF is the compressed version of BTF is about 3 or 4 megabytes, which is big if you need to have hundreds of thousands of BTFs in your Docker or your package. But the BTF hub and the community created tools to minimize the BTF. The BTF itself contains information for every struct and field in the kernel, but eventually our program uses few of them and doesn't need all the information exists. So the minimizer tool gets the BTF file and your eBPF program, and just generate a minimized BTF that weighs only a few kilobytes, which gives you the ability to send dozens and hundreds, thousands of BTFs along with your Docker or package management. And by that, we are able to achieve broad coverage. Still not perfect. And this is why I mentioned before, we have a fallback mechanism, because we still have agents, kernels without BTF, or we have old agent versions that are running on it wasn't shipped with all BTFs that we have. For example, our latest, every time we are releasing a new agent release, we are generating or pulling all BTFs for all known BTFs as of today. So if tomorrow there is a new Linux patch for 4.14, our older versions would not support or will not have BTFs for that kernel. For that, we still need the run compilation and offset guessing as a fallback mechanism.
Let's talk about that. Let's talk about runtime challenges. So BTF, offset guessing, runtime compilation, these are all the ways that we achieve the portability of these probes, right? Which is, the goal of which is always to instrument something and have it be universally deployable. It sounds like a really nice dream, right? A very, very cool idea that we came up with years ago now, and now we're finally seeing it implemented in modern version of the Linux kernel in a way that we can really leverage as somebody who provides observability services. But let's talk about just running these things on the system itself.
So as Guy showed us in previous slides, we have a good amount of challenges that we need to face to develop and deploy the eBPF programs on the wide variety of our customer environments. But unfortunately, it doesn't end there. Like, even once we are able to support most of the environments and create this portable version of our eBPF programs, there are still challenges that we need to face in the runtime. And I'm going to mention a couple of them and show why it's challenging for us and how we are trying to improve our situation. So first of all, Linux kernel, as I said, is always evolving, and same goes for the eBPF subsystem. So as being such, there are new features that being added to new kernel releases. In most of the cases, those features are not really backported to older kernels, since those are not like security patches, it's just new functionality. And again, fortunately for us, we need to support a very large customer base, and many times we are actually facing older kernel versions. So for Datadog products, we need to find this right balance between utilization of these new features, which usually help us to improve performance or simplify our code base. But also we need to support those customers that have the old kernels and we cannot use those features. In order to overcome those, we are utilizing dynamic feature enablement. Basically, we are trying in runtime to understand what kernel version we are running on, and then we have sort of like conditional switch case, like which features can we use. For example, a good example for that would be a very common data structure for eBPF, which is called per buffer. It's a data structure that allows us to share data between kernel and user space. In kernel 5.8, there was a new data structure called ring buffer that was introduced with a significant improvement in performance. But unfortunately, before that, this feature didn't exist. So we are utilizing this feature when we are able to, but we also need to support the per buffer implementation. Having said that, yeah, sorry, go ahead.
This has always been a challenge, right? These buffers and kind of event storms and getting events out of order when a system is very busy and it needs to emit a lot of metrics, right? Like that's been a classical problem, I think, in monitoring on Linux for ever and ever. But like how do you deal with these features versus breaking changes and then maintaining that backwards compatibility?
Yeah, so you are very accurate. There are some challenges that over the time these new features are trying to solve already internally as part of Linux capabilities. And that's, as I said, like once we are able to use them, it significantly reduces the amount of code that we need to implement as our custom business logic. And so one example, I think you mentioned it as event ordering. And I think I'll stick to that in order to emphasize more on this per buffer, ring buffer example. So eBPF is basically push-based technology. Basically, we are listening to events happening in kernel, and then we have different handlers based on different events. This can happen asynchronously, and those events can arrive asynchronously. But many times for our products, we actually need the right order of those events in order to perform some logic. So for example, whether it's like process start and exit times or network connection lifetime events. So proper ordering is very crucial for our products' actual application logic. Using per buffer, we need to implement this code on our own, usually in user space, which adds, of course, additional overhead. And then we need to make sure that we are not using too much resources of the target machine. As I mentioned before, after all, we are running in customer environment. When we are able to use the ring buffer, this is actually already solved out of the box for us, and ring buffer by nature solves this logic by using its internal structure. There are some other examples that we need to face that can create potentially breaking changes. It doesn't happen very often. Usually eBPF features are actually developed in a proper way without breaking changes. But sometimes the interaction or integration of eBPF subsystem with other moving parts can create such scenarios. I think one very popular example across a lot of eBPF projects, whether we face it at Datadog, but also many open source products has it, is at some point Golang programming language introduced a breaking change in their ABI. I think it was when they switched from Go 1.16 to 1.17. Basically, they broke the function signatures, well, changed the function signatures, and started to pass the parameters via registers and not on stack. eBPF allows us to hook also the user space by using uprobs. I'm not going to deep dive into that too much. You can watch, I think, the previous episode about it. But uprobs allows us to put the hooks on user space area. And of course, when the function signature is changed, these uprobs will not just work out of the box. So you need like to make adjustments in order to make them work.
Makes sense.
Yeah, this slide I created just to show, I don't know if it's like big enough, but basically I wrote it from the BCC repo. It's actually a very nice list of core features and core data structures that are used in eBPF. And you can see here over the time with new Linux versions, there are new features introduced. And as I said, like we are trying to utilize the new functionality when we can, but we also need to work in these areas where those don't exist.
And then this next part, the next slide, becomes super important, right? As we think about, maintaining functionality across all these kernel versions, because not only do we want to make code, ensure that it will work, ensure that it's very, very portable and highly performant, we also want to make sure that it's not going to crash anything or cause a negative impact to the system, right? And that's where this verifier comes in.
So in some sense, you're right, but actually the sad fact is that it doesn't matter what you will do at the end, you need to pass the verifier, otherwise you just can't run on the host machine. So you don't have much of the choice. And that actually creates another limitation or sort of boundaries on the eBPF development lifecycle. Basically, eBPF programs that are run in kernel context and they can access kernel memory. So actually, to avoid some extreme edge cases and avoid endangering the operating system, their eBPF subsystem is running those programs in sort of like a sandbox environment. And for that, part of the subsystem, a crucial part of this subsystem is a component called eBPF verifier. It was covered a little bit also in the previous episode. It acts sort of as a gatekeeper to ensure safe conditions for the eBPF program execution. That means that when we develop these eBPF programs, we need to meet certain requirements and criteria to be able to run them successfully. Otherwise, they will be just rejected. For example, we cannot have the program has to be like a DAG, which is directed acyclic graph. Basically means like no recursion, no go-to statements. We have to check all the dereferences. We cannot have like null pointers. Basically, there are no loops allowed, which was actually changed over the time. I will touch it in the next slide. And the no unreachable code. This is just a few examples, and there are much more.
Those all seem like very good guardrails to have implemented, not just for eBPF, but for any body of code that you would need to be highly performant.
Yes. So eBPF allows you a lot of flexibility and a lot of power, but again, you're running in a very sensitive environment, and you must have some sort of like protection not to make damage to the entire host. So in this slide, I'll discuss like also the involvement of the verifier, similar to the functionality of eBPF. So the verifier is evolving over time, and basically kind of like converts from a very strict to a more flexible gatekeeper. So some examples before, like in older kernels, you had a very small limit on the number of instructions for eBPF for your eBPF program. It was 4K, 4096 instructions. It was raised to 1 million, which allows you much more flexibility of what you can do in kernel logic. And as you can imagine, if you move more parts to the kernel side, then it potentially you can improve the efficiency of your program. In kernel 5.3, finally the verifier started to allow bounded loops. So basically, you can have loops; they have to be limited in the number of cycles. But it also really simplifies the code that you write for your eBPF program. We're still treating the verifier as sort of a black box. Basically, if you look at the source file that I added a link in the slide, you will see it's like one file in the Linux kernel source with a little bit over 20,000 lines of code. And up until today, like the best way to know if you can run or not is just actually trying to run your program. And if you are able to load it, then you're past the verifier. I have to mention there are few attempts were made, and it's still a work in progress to try and decouple the verifier from the kernel and create sort of emulators that will allow faster development and testing cycles. But those are still not widely used as far as I know.
Sounds like an opportunity for some great dev tools.
Definitely, that will really simplify our lives as eBPF developers. Yeah, this slide is actually a bit amusing. I literally put here some actual examples from the open source Datadog agent code base, just to demonstrate how the production code must be adjusted sometimes just to pass the verifier check. So for example, in the upper screenshot, you can see that we have a struct that stores IP address for source and destination, but unfortunately we cannot use one variable of 128 bits. It just doesn't work well with the verifier, so we have to break it into two different variables and then perform sort of like bits arithmetic in order to build the full version.
Anytime that there's a static analyzer, there's always a workaround.
Right. So we are almost out of time, and I think we are towards the end of the presentation. Just to mention one of the things that we recently started as internal in-house project to improve developer experience. We call it kernel matrix testing, or shortly KMT. It allows us to spin almost any kernel version or any distribution very fast. In order to do that, we are utilizing virtualization, QEMU, and micro VMs and it allows us to cover most of the Linux distros and kernel versions. We are integrating this solution in our CI to be able to perform like quick sanity tests on our eBPF programs, but we also allowing our developers to spin these machines, sort of like a local development use case to track the problems fast.
And this is something, right, that we may be open sourcing in the future, or attendees could look for a write-up coming?
Yeah, definitely. Follow us, and I think like we are going to share it as open source and create some write-up about it in some future once this will be like a bit more mature.
Very cool. I think last but not least is that, Datadog is a contributor back to the overall eBPF ecosystem, right? We have all of these great contributions and examples that other folks can look to and learn from. Anything that you want to call out from this list?
Well, Datadog agent is an open source repo and is actually a very large repo for good examples of like production ready eBPF programs that people can look and even try. So we also launched on Open Source Hub. I think keep an eye on that, and we are going to post there some cool projects also related to eBPF. Not only, but there will be definitely some dev tools there.
All right. Yeah, make sure to check out the Datadog Open Source Hub. It is newly launched and is the best place to see Datadog's contributions back to the open source community, as well as just some spotlights on cool open source features kind of across the Datadog GitHub organization. With that, we don't have any questions in the chat, but we have a couple minutes to take questions if anybody wants to ask a question of either of our panelists. If not, thanks for being here today. You can check out datadoghq.com/careers to see all the great opportunities in engineering and beyond at Datadog. Special for this episode, though, if you want to just track this link, we actually have several roles open at Datadog now inside of this ecosystem that we just presented on. So if these topics are interesting to you, you're passionate about any of these things, the challenges that we just discussed in the episode, we'd love to hear from you. And with that, thank you so much for attending today's episode of Datadog On. We'll see you here next time.